Welcome to EGME-331 Solid Mechanics. In this video, we'll be discussing about deflection of beams. Now, what's deflection of a beam? So it's basically the deformation of a beam when it is subject to a external force. Now, the excessive deflections. The beam always deflects. So beams are designed to deflect. If it doesn't deflect, it would break. So what we are seeing here is excessive deflection. That means a deflection that is causing concerns for the designer as well as for the people who are using that particular structure. Let's say door, because of the deflection, it doesn't close. That's an excessive deflection. So what we consider as a designer is to specify a maximum deflection. So once again, the beams are meant to deflect within a specific range. So a satisfactory design would be designed such a way that it would limit its maximum deflection on top of the minimum load carrying capacity. Beams are designed to carry loads. So the maximum deflection is what we are interested in this particular topic. Now the deflection depends on several things here. Most importantly, the stiffness of the material. What stiffness of the material? It's nothing but the Young's modulus or elastic modulus of the material and the cross-sectional area of the beam. So if you vary the cross-sectional area of the beam, you would see a different deflection values. There are different ways to calculate beam deflections. The most popular one among them is the integration method. Now, let's try to understand the coordinate system here. So we could consider a simply supported beam. We could see that in this particular case, we are using a positive bending moment because the compression is on the top and the tension is on the bottom. So the sign of the bending moment creates directional changes in the stress. So the beam deflection is denoted by mu. If you take the first derivative of deflection, we get the slope of the flexural curve or the bending curve. The second derivative would be the bending moment. The third derivative or the first derivative of the moment, bending moment, would be the shear force V. And if you take the fourth derivative of the deflection, we would get the applied load. Here that EI is what we call as a flexural rigidity, which is a material property for that particular beam. You can see the figure over here. If you start with the applied load P, you could go backwards. So let's start with the deflection. If you take its derivative, we'll get the slope, and then we take one more derivative, we get the moment, and so on, and we reach the load. So in case of integration method, what we do here is we start from the load, we could integrate, and we could get the successive quantities, the shear force, bending moment, slope, and then finally the deflection. What we need for this integration, we will see in the next slide. So we need the boundary conditions, the continuity conditions, as well as the symmetry conditions. The constants must be evaluated from the known conditions. And this integration approach is the most common method to determine all those quantities, including the beam deflection. We need to understand what are the boundary conditions here. This will be the slope and the deflections at the limits, the point where it gets supported or no support. So you can see here there are different kinds of support that are commonly used. For beams, we have the pin support, roller support, and the fixed support. In case of pin support, the deflection would be 0. Roller support, we have the deflection once again 0. And for fixed support, we have the slope as well as the deflection to be 0. Similarly, we have the continuity condition as well as the symmetry condition. In case of continuity, what we see here is we consider the changes, the abrupt changes. So wherever there is no abrupt change, we consider it as a continuous structure or a continuous segment, and we could easily determine the quantities, the deflection, the slope, the bending moment at each of those points on that particular segment. So continuity basically ensures that the beam is a continuous structure. Wherever there is a abrupt change, that's where we need to determine the next quantity. Symmetry, similarly, because the beam can be configured so that there will be symmetry, it will be easily possible to determine the slope of the beam at certain locations because of the fact that it has a symmetric arrangement. Now to do the double integration, we need to sketch the beam, needs to estimate the reaction forces, find the equilibrium condition, and then perform the integration. Again, this is a double integration method, so you would be starting with the bending moment equation and then integrate it twice, and we would eventually find the quantity deflection, which is mu, followed by using the boundary conditions to determine the value of the deflection. So you use the boundary condition, the continuity conditions, determine the constants, and then we can determine the curve or the slope of the bending beam. Here we can see an example. We have a cantilever beam which is subject to a load at point P at the end. We are asked to find the elastic curve at point A on the beam. Now we are given that the quantity EI, which is a flexural rigidity, is constant for this particular beam. You could see here we take that section of the beam and we have the load P that's applied. We have the equation EI d square V by dx square, which will be equal to negative of Px, where P is applied load, and if you integrate it once, we would get the slope followed by the second integration, and we could get the deflection, that nu, followed by evaluation of constants. We have the first integration leaves us with the constant C1, and the second integration we get two constants, C1 and C2, to determine the constant. At the point L, we know the slope would be equal to 0, so we could determine the constant C1. C1 would be PL square over 2, and then again at point L, the deflection would be equal to 0, with which we could calculate the second constant, which will be negative PL power 3 over 3. So if we substitute the two constants C1 and C2 back into the equation, we could calculate the equation for deflection and the beam slope equation, as we can see here. And to determine the deflection slope at A, we have to put the value for x here. X would be 0 at A, and we could get nu, the deflection at A would be equal to negative PL power 3 divided by 3 EI. And as far as the slope goes, at the point A, when x is equal to 0, we get PL square divided by 2 EI.